Welcome to today's video on Cambridge IGCSE Mathematics for the syllabus codes 0607 and 0580. Our topic for today will be probability, where we will be looking at the subtopic probability applications. Probability is the chance or the likelihood of an event happening, and we actually use it in every day when making decisions. Examples of probability include the probability of obtaining a head when tossing a coin, or the probability of obtaining the number 6 consecutively when rolling a dice twice. We use the principle of symmetry if all of the outcomes are having an equal likelihood of happening. For instance, if we want to find out the probability of rolling a 4 using a fair dice, what we can do is we can first list out all of the different outcomes that we can get using dice. So that's the numbers from 1 to 6 if we use a regular dice. And now if I want to find out the probability of obtaining a 4, I can see that there's just one event that I can get a 4 in. So that's 1 divided by the total number of outcomes that I have. And in this case, that's going to be 6. So the probability of rolling a 4 using a fair dice is 1/6. We can assume that a trial can have n number of equally likely outcomes, and then if we consider that the success can occur in s ways, then the probability of success is p, and inside brackets we can write success is equals to s divided by n. And I can apply this to the previous example that we also did. So the probability of success was 1 out of 6 totally equally likely outcomes. So the probability of success in our previous example was 1/6. If I have an event that cannot happen, then the probability of it would be 0. If I know that an event is certain to happen, or it has 100% chances of occurring, then the probability for it would be 1. And all probabilities that we have would always lie between 0 and 1. We can also use relative frequencies as estimates of probability. So the relative frequency can be defined as the number of times an event occurs divided by the total number of events occurring in a given scenario. So the relative frequency is the number of positive trials divided by the total number of trials conducted. Let's have a look at an example on relative frequency. If a cubical dice is tossed 30 times and lands 5 times on the number 6, what is the relative frequency of observing the die land on the number 6? So to begin with, I'm just going to go ahead and write down the equation of relative frequency that we know. So that's going to be the relative frequency is equals to the number of positive trials divided by the total number of trials. In this case, I can see that the number of positive trials is 5 and the total number of trials is 30. I'm going to go ahead and substitute those values in here. So 5 over 30. And I can simplify this if I want to as well. And this is going to simplify down to 1/6. So the relative frequency of getting the number 6 is 1/6. Next, we're going to look at estimated probability. So estimated probability is for trials that have categorical outcomes, which is simply just noting the presence or the absence of a specific term. And one way to estimate the probability of an event from the data that we have is to simply count the number of times an event is occurring and then divide that by the total number of trials. So the estimated probability is the number of times our event has occurred divided by the total number of trials. Now let's look at an example on estimated probability. So over here, we're going to consider an experiment of rotating the spinner 50 times, and the table shows us the results of the experiment conducted. What we need to do is to find out the estimated probability of spinning the color blue. So we have 4 different colors, and the table gives us the amount of times that we have these specific results. To find out the estimated probability of obtaining the color blue, what we're going to do is we're going to see the number of times we obtain blue, that's 10, and then divide this by the total number of trials conducted. So to work out the total number of trials conducted, I can add up all of the different occurrences. So that's 11, 10, 13, and 16. And this is going to give me 50. So my final answer would be 10 divided by 50, which I can simplify down to being 1/5. Something else that we can remember here is that probabilities don't always have to be given in the form of a fraction. We can also show this in forms of a decimal, which in this case would be 0.2. Or if I wanted to, I can also convert this to a percentage. And to convert a decimal into a percentage, I just need to times it by 100 to give me a value of 20%. If we need to describe the probability of an event occurring, we can use mathematical notation to show that. So to show the probability of an event occurring, we would use an uppercase P to represent the probability, and after that, we can describe our event inside brackets. So let's have a look at some examples. A fair dice is thrown once, and what we need to do in this question is find the probability of obtaining a 6. So in this case, we know that if we're using a fair dice, we have a total of 6 outcomes. That's the numbers from 1 to 6. And P, obtaining a 6, means the probability of obtaining a 6. So how are we going to solve this? I know that obtaining a 6 can be just one outcome. That's just one outcome that we have out of a total of 6 outcomes. So the probability of obtaining a 6 is 1/6. Moving on to the next part of this question, find the probability of obtaining an even number. So when we roll a fair dice, we have outcomes from 1 to 6, but our even numbers are the numbers 2, 4, and 6, which is a total of 3 outcomes. So the probability of obtaining an even number is 3 outcomes out of a total of 6 outcomes, and I can simplify this to be 1/2 or 50%. Then finally, what's the probability of obtaining a number greater than 3? Again, we need to list our possible outcomes. On a fair dice, the possible outcomes for a number greater than 3 would be the numbers 4, 5, and 6. So again, there's 3 possible outcomes out of a total of 6 outcomes, giving us the answer 1/2 again. Mutually exclusive events are 2 events that cannot occur at the same time. So either event A can happen or event B can happen, but both events A and B cannot happen at the same time. So if they show this on a Venn diagram, I can see that event A and event B are 2 entirely different sets here. So the probability would be of event A occurring, or the probability of B occurring would be the probability of A union B, which would be the probability of A and the probability of B. An example for mutually exclusive events would be the probability of rolling an odd and an even number on a fair dice. If I roll my dice just once, I know that I can obtain either an odd number or I can obtain an even number, but I cannot obtain a number that's both odd and even. In this case, these events are mutually exclusive and they cannot occur at the same time. So let's look at an example consisting of mutually exclusive events. So here this question is asking us, what is the probability of a dice showing a 2 or a 5? I know that obtaining a 2 or 5 is mutually exclusive events because on a dice I can either obtain a 2 or I can obtain a 5, but I cannot obtain both together. So when I want to find the probability of the dice showing a 2 or a 5, we can use the formula that we just looked at. So the probability of obtaining a 2 or 5 would be the probability of obtaining 2 plus the probability of obtaining a 5. Now, the probability of obtaining a 2 on a dice is 1/6, and the probability of obtaining a 5 is again 1/6. So the probability of obtaining a 2 or a 5 is going to be 2/6, which I can simplify down to be 1/3. Next, we're going to look at independent events. Independent events are two events which the occurrence of one event would not affect the occurrence of the other event. So in these types of events, I can see that A and B can occur, but the occurrence of A would not affect the occurrence of B. And when we have events that are independent events and we want to find the probability of A and B occurring, then this would be the probability of A times the probability of B. An example of independent events is if I toss a coin twice, then the probability of obtaining heads on the first toss would not affect the probability of obtaining a tails on my second toss. So these are independent events. Let's look at an example of using independent events. So the question here tells us that bag A has 8 red buttons and 4 green buttons, while bag B contains 10 black buttons and 5 orange buttons. One button is taken out from each bag. Find the probability of selecting one green button from bag A and one black button from bag B. So initially, I'm going to figure out the probability of selecting one green button from bag A. I can see that selecting a green button from A and selecting a black button from B are independent events because the probability of selecting a green button from A does not affect the probability of selecting a black button from B. So to select a green button, the probability of getting a green button from bag A would be 4 out of a total of 12 outcomes. So I know that 4 outcomes or 4 buttons are green and 8 buttons are red. So I have 4 green out of a total of 12 buttons. So 4/12 is the probability of selecting a green button, which I can also simplify down to being 1/3. Then I'm also going to find out the probability of selecting a black button from bag B. The probability of selecting a black button here. And this is going to be 10 out of a total of 15 outcomes, because I know that I have 10 black buttons, but a total of 15 buttons. Then I can simplify this down to being 2/3. Finally, to find out the probability of green from bag A and black from bag B, I would just have to go ahead and multiply their individual probabilities. So 1/3 times 2/3, which would give me a final answer of 2/9. Something else that we can remember is that whenever we have to find AND probabilities, we generally have to multiply because that's showing us independent events. But if we have to find all probabilities, then we would have to add because that's showing us mutually exclusive events. So the wording of our questions can be very important in helping us recognize which equation we would have to be using. Let's also have a look at an exam style question on probability. So the question reads, Jane throws a biased coin. The probability of getting a tails is 0.4. Work out the probability of getting heads. Now, although we know that the coin is biased, there can only be 2 possible outcomes when we toss a coin. We can either obtain a heads or we can obtain a tails. And the total probability of obtaining heads as well as tails should always equal to 1. So we can use this to form an equation. So that's the probability of obtaining heads plus the probability of obtaining a tails should add up to 1. In the question, we know that the probability of getting a tails is 0.4. So we can go ahead and substitute that in here. And now we can work out what the probability of getting a heads here would be. So that's 1, take away 0.4, giving us a final answer of 0.6. So that's our option 3 over here. And there we go. That's how we solve questions on probabilities. Thank you.